Welcome to Power System Experts. This is our session on study of a Type 4 wind turbine in PSCAD. We have a pre-model case here. So let's open PSCAD. Go to PSCAD, open, and open your wind turbine Type 4 workspace. So it's open now. You see there are two files in our case. The one is an average model and the other one is a detailed model. We are currently viewing the detailed model and we will discuss it first. So on the page you can see a Type 4 wind turbine. It's connected to the grid through this POC bus, point of common connection bus, through a YY transformer. If you double click on this transformer and check its winding voltages, its V source on one side and V base on the other side. Here you can see V source is 230 kV and V base is 33 kV. So it's a 33 kV to 230 kV transformer. The short circuit ratio of the grid at point of common connection bus is 10, which means a very strong grid. The fault is connected to the POC bus with fault type control and fault time control. This monostable controls the duration of the fault. It's 150 milliseconds. And this dial switch selects the file type. Here are fault type 1, fault type 4 and fault type 7 selected. If you want to know the details of fault type 1, 4 and 7, just click on the fault, go to its help. So here you see that fault 1 means phase A2 ground fault, fault 4 means phase AB2 ground fault, and fault 7 means phase ABC2 ground fault. So this is the control panel for this fault type. You can select it 1, 4 or 7. Here the 4 is selected for default, and using this on off switch you can enable and disable the fault. This this control panel controls this select switch, which controls the monostable. We will check the response of the wind plant for a fault using these blocks. So here on the right side of the page you see wind speed adjustment slide bar with its control panel here, and also there is a blocking and deblocking delay block. This delay block is set for 500 milliseconds. It means that this deblock signal will be activated after 500 milliseconds of start of the simulation. This is done so that the solar plants become active after when the grid voltages have become stable. So right click on the wind turbine icon and select its edit parameters to see its parameters. The first set of parameters includes blocking and deblocking signal that we have just discussed here, and the nominal frequency of system, it is 60 Hz, and the total number of wind turbine generators is set to 100. You see here it's set to 100 through this data label. It will be used in the scaling component, which is inside the definition of this Type 4 wind turbine, which we are going to explore. And the rated power of the solar plant is set to 2 MVA, and the rated RPM is set to 12. The third set of parameters is wind speed, which is set by this wind speed setting slide bar, and the cut-in speed and cut-out speed are 3 and 25. The cut-in speed means that the wind turbine will become active when the speed is greater than 3, and it will be cut off or deactivated when the wind speed crosses 25. This is modeled in order to save the wind turbine from damage. And the fourth parameter group is related to permanent magnet machine. The rated voltage is set to 0.69. It's shown here, and the base machine frequency is set to 30 Hz, and the transformer HV rating at point of common coupling is set to V base, and we have already explored that V base it's equal to 33 kV. And now double click on the wind turbine to see its detailed definitions. The wind plant consists of three main parts. The first part is this electrical system, which consists of this grid side converter, this machine side converter. Their controls are modeled here, and there is a DC link between the grid side converter and machine side model, and also there is a DC chopper connected to this DC link to protect it from over voltage. There are AC filters connected on both converter sides, and there is the wind turbine model, and here is the permanent magnetic machine model. These two are mechanical systems, and this one is the electrical system. And this permanent magnet machine, it is linking the mechanical system with the electrical system. The wind turbine models the mechanical power and torque obtained from wind speed and pitch angle controller. Right click on this module and select edit parameters to see its parameters. So the power generated output PGen, this PGen is the power generated output from this mechanical permanent magnet machine, and its wind speed WPU. These are input to this wind turbine as a feedback signals, and its output is wind wind torque and reference power. And we will talk about this S2T mode signal later. And V wind is the speed of the wind, which was coming from the previous from the main page that we have seen. Exploring its parameters, you see everything is quite simple here. The cut-in speed, the cutout speed, the KP pitch, and the TI pitch for the PI controller, they are coming from here, and they will be used inside the pitch controller, which is inside this wind turbine, and we will explore it in a while. There are some machine parameters relating to this machine, which are given to this model. They will be used inside its definition. And the turbine parameters is radius, turbine RPM, and machine nominal speed, maximum and minimum pitch angle. These are also set here. Okay. We double click on this wind turbine to see its internal definition. Here you can see that this is the pitch angle controller. This one is the pitch angle controller, and this model, and this is the mathematical model of the wind turbine. And after and this mathematical model of wind turbine generates two signals, which is the reference power and the reference torque output. These are inputs to the permanent magnet machine, and it generates electrical power from these two signals. So going back, now we will explore this permanent magnet machine. The wind torque and reference power generated by this wind turbine are inputs to this permanent magnet machine. If you click on it and check its parameters, you see that the name of identification, rated MVA, rated voltage, rated frequency, and multi-mass interface, these disabled. These are its parameters. And if you see its machine data, you see that its winding parameters are mentioned here. Winding resistance, its leakage reactances, And damper wire properties of its damper windings is magnetic strength, angular momentum of inertia, and machine damping. Everything is mentioned here for this permanent magnet machine. And when you check its internal outputs, these are mechanical speed and electrical torque. And you see here that W per unit is also coming here from this permanent magnet machine as a feedback signal. And this signal PG is the power generated here on the grid side converter. If you check here, this active power is named as PG, and this signal is being used as a feedback in this wind turbine model. So talking about this AC to DC and then DC to AC converters, the grid side converter control this grid side converter this controls the DC bus voltage, while the machine side converter this controls the active power at the terminal of this wind turbine output. In this example, both converters operate as voltage source converters, and both models are modeled as detailed switch models. Both machine side and grid side voltage source converters have their separate controllers. You see them here. And the function of this controller is to provide reference time domain voltage signals, which will be compared with a triangular carrier to generate a sinusoidal pulse with modulated firing pulses for the inverter switches here. Another component used here is the DC link chopper, which is used to protect the DC bus from overvoltage. Right click on this and click edit parameters to its parameters. So the base voltage for it, the base power for it, its activation voltage and maximum DC voltage is given here. If we want to check its definition, just double click it. So here you see that an IGBT in series with this discharging resistance is here. If the EDC voltage this exceeds the maximum per unit set from these parameters, then the IGBT switch is turned on by this hysteresis switch, hysteresis buffer, and it keeps and it remains on until the DC voltage falls below the VDC base. In this way, the voltage is regulated on this DC link. So going back, AC filters are connected on both the voltage source converters to remove some of the voltage harmonics of the voltage source converter from entering the grid and into the permanent magnet machine. And there is this coupling transformer, is delta Y transformer, and then so this scaling command emulates a situation in which some say for example 100 such systems are connected to this grid. On the top of this page, you see the sequence time for switch, converter unblocking, and machine torque control modes. So we already know that this D-block signal it gives a delay of 200 or 500 milliseconds from start of the simulation, and after that this BRK signal, this will turn on this breaker, and with a delay of let's take this delay, it's 100 milliseconds. So with a delay of 100 milliseconds after the breaker, the grid side converter, this is activated. This is D-block grid signal, and after another 100 millisecond delay, the machine side converter, it is activated, and after a delay of 500 milliseconds after the machine side converter, so this S2T mode, this is activated, and that this permanent magnet machine is activated to operate in torque control mode. So if you want to see the detailed model of switches, just double click here, and here you can see that the inverter is modeled as six discrete IGBT switches, and here is the pulse generating blocks for it. The PWM block, you see that here there are comparators and AND gates and other logic blocks for generating the SPWM signals. But if you go to this average model and this wind turbine, and check its voltage source converters. Here you see that the inverter, three-phase inverter, is modeled as dependent voltage sources instead of IGBT switches. So the advantage of this is that our simulation time is saved, and the simulation is almost say 7 to 10 times faster than the detailed switch model. So this is the only advantage of the detailed of the average model, that it saves your simulation time. But the detailed model, it gives a real or practical view into whatever will actually happen in case of a transient or a fault in a wind power plant. So now let's run this simulation, and we will observe the effect of a fault on this wind turbine dynamics. So let's run the simulation, and the simulation is running. Yes. So the simulation running has started. You see that the voltage at the POC is rising, and now the voltage is stable against wind turbine speed of 10. Okay, the wind turbine is activated here after a delay of 200 milliseconds. Let's wait for these signals to get stable, the active and reactive power from the wind turbine. Okay, they are now pretty much stable. Let's implement a fault here. The fault goes, and the duration of the fault is, we see that is 150 milliseconds. So you see that during this fault, this POC voltage at the POC, the power of wind turbine, it went from about 200 to 100 megawatts, and the inverter power, the reactive power, went up from about say 22 megawatts to more than 30 or more than 30 megawatts here, and the voltage at the POC was dropped down to about 0.7 per unit during this fault. So now let's see the dynamics against changes in wind speed. So the wind speed is 10 here, so we increase it. Now let's decrease it. Okay, we have decreased it to 0.78. Let's refresh this graph. Okay, the wind speed has decreased, and you see there the voltage at the POC is constant, and there is no glitch in it. But the active power, there is a small glitch in the active power at the output of the wind turbine, and then the feedback and the controller, which controller compensates it back. Let's decrease it further to 9. So it's less than 9 now. Let's refresh the graphs. You see that the output power at the wind turbine generator has decreased now. The voltage is constant. The reactive power has is also the constant. So now the voltage power at the output of wind turbine generator has decreased. So let's go to the average model and try simulating it, and we will check the difference between the detailed and average model. Yeah, the simulation has started now. Let's wait for the signals to get into steady state. So the wind turbine is activated now here. It is providing about 200 megawatt active power and some 15 megawatts reactive power. It's increasing. So it's increasing. So it's almost a constant. So let's now give a fault here. The fault type is set to 7. It's a 3-phase fault. Okay, so you see that in the average model, the power output at the wind turbine has almost gone to 0 during this fault, and after that everything has recovered to the normal state. In this way, if you check the wind speed dynamics, we are decreasing the wind speed to almost 8, and you see that there is the behavior of the power in this case is very similar to that one in the detailed model, but this simulation it's much faster than the one from detailed models. So that's all for today's lecture about study of a type 4 wind turbine. So the wind turbine can be modeled as a detailed model or an average model for dynamic study of fault at the point of common coupling and the dynamics of the wind speed. Thank you very much.